Hello, everyone. Hope you're all doing well, making it through midterms. I don't have any announcements for today of any changes or anything new for the course. Any questions about anything? The mic is particularly loud here. Great. So today we're going to cover. We have two sections left for vector loop method. That's generating equations. Today we're going to talk about generating solutions using two loops instead of one. And I know those of you who attended the tutorial or saw the video, Taha covered a problem with two loops. And I had him go through that full problem to kind of give you a nice overview of the full solution for a more complex mechanism. Today we're going to sort of take a little step back and look at, in particular, the big question is, when do I need two loops? When can I use one loop? And in fact, a lot of times when one loop could solve the problem, solving it with two loops turns out to be easier or a more straightforward solution. So we're going to look at an example of that today. And hopefully after today, you'll be empowered to choose and design loops for mechanisms. The last topic for vector loops, which we'll cover in the next lecture, is about mechanisms that have two solutions. So two possible configurations for a single input. So we'll get to that next time. So before we do this, I'm going to show you an interesting mechanism. This is a little aside. And this is a mechanism called a rocker bogie. A rocker bogie, it's a unique kind of mechanism. And it's not used a lot. But where it's used really commonly is for rovers on the moon or Mars. This is the Curiosity rover, which went to Mars in 2012. There's another version of it, which is very similar, which landed in 2021, called Perseverance, I think. Perseverance is the name of the lander. It's almost the same rover design with updated scientific instruments and some other things. It's a NASA, a NASA project, although there is a Canadian instrument on board that University of Guelph designed and sort of operates that instrument. It's a spectrometer on this big instrument arm. That instrument arm has like a whole enormous payload of all these scientific instruments that this rover can go up to interesting rocks and point different scientific instruments at them and do things like digging into the rocks. This thing moves with motors inside the wheels, which is a little bit simpler design than other ways of connecting motors to the wheels with axles and gears and things like that. And the reason for that is that the design of the suspension is this thing called the rocker bogie. Rocker bogie. It's a little dark up there. There we go. So the rocker bogie is this really strange way of connecting the wheels. And they're all connected to the body of the rover up here. And there's a mechanism. There's one link there. And it's connected to the front wheels here. And then the back wheels are connected back here. So this is a rocker bogie mechanism. And the reason that this mechanism is used, and not just on this rover, but also it's used on all these other NASA missions, and this year a Chinese rover landed on Mars. I don't think the Chinese one uses the exact same kind of mechanism. I wasn't able to look into that one too detailed. But these other ones all use the rocker bogie, just in different geometry, slightly different shape of the same kind of rocker bogie mechanism. And the reason this is used is because it can allow the wheels to move up and down really large distances. So you have 6 wheels, and imagine if each wheel had its own kind of suspension. To be able to kind of absorb these inputs. And the cool thing is that one leg can go way up high, right? One wheel can go way up high while the others stay on the ground. And the mechanism kind of averages out all 6 wheels' heights. And the body, which is going to be attached to that yellow link, the body is kind of stabilized. It takes kind of the average angle of all the wheels, and it allows it to go over these huge obstacles. I was looking for videos of like little ones that people built. it's very simple. Like you could build one, put a motor in one or more wheels. If you power all of them, then it's really good at going up over obstacles. And you can see it really excels when one wheel hits something but the others don't. And that makes it pretty unique from other types of suspensions. You know, this isn't used for like automobiles because it's a really different condition. If all of your wheels are moving on flat surfaces, it's a little bit, you know, it's a large mechanism. There might be other downsides of having this mechanism compared to a regular mechanism for suspensions, where each wheel is more independent. So thinking to MIE 301, like this is a mechanism, right? So we have an input, which is the wheels moving. You can turn the motor on one or more wheels and get this thing to move forward. So this is a typical kind of task that if you were on the engineering team controlling this, you drive this up to a rock, right? And here there's some rock of interest that the geologists identified, and we want to take a laser scan of that. So this instrument here points a laser and vaporizes some of the rock, and then there's some sort of spectrometer that looks at the dust that comes out and analyzes the chemical structure of that dust. So you want to aim this thing, and let's say we want to move the rover a little bit closer, right? You might ask yourself, how does the inputs to the wheels affect that laser, the aim on that thing, right? So that would be it's a complicated geometric problem. There's all these inputs. If we're just thinking about one side of the rover, you could say, okay, we have these 3 wheels on the ground, and then one basically output, which is the laser, which is also has the camera on it, which goes up and down, attached to the body. So you could pose this as an MIE 301 problem, and you could study it using our tools exactly. So you could say, okay, we have some motor speed as the input, and all these wheels are coupled together, right? If you assume that they're not slipping, if one of the wheels moves forward, all of them move forward. So you could say, okay, the mechanism, assuming the body can't you know, twist on its own, the mechanism would have a mobility of 1. So if you put some motor speed input, the camera angle output is going to have some one-to-one relationship. So you can calculate that directly, and you could study this. I think I put this on a past midterm, something really similar to that question there. So that's an interesting mechanism, kind of a standalone mechanism. Oh, I forgot to show you the video. Maybe you've seen these videos of this thing landing. It's like the coolest spacecraft landing. It's like a sci-fi thing, but they really did it this way. So here's they sent this orbiter and the rover to Mars, and here's the rover inside this little capsule here. And Mars doesn't have a very thick atmosphere, so it's actually difficult to slow it down. So they can do some slowing just by the air drag there, and it'll release a parachute in a minute. But the final slowdown, because they want to drop that rover, which is complicated and fragile, so they want to drop it onto the surface gently and not just kind of crash in like some of those smaller previous rovers. They actually like crash land them with a big airbag, and they kind of bounce, and then the rover drives out. But this thing's like bigger than a car. It's a really big rover. So that was, I guess, deemed not feasible. So anyway, they put all these rockets on it and slowly descend. And the coolest part's coming here. So they have some kind of autonomous guidance, so the system can watch the surface and look for a good landing spot. So they like descend the rover on these cables. I think they call it the sky crane. I think this is really ridiculous and awesome. And so they just kind of set this thing down softly. And so here the legs are deployed, and they use just the suspension. That's the rocker bogie suspension there. They use that to just you know, put a real soft touchdown. And then after it releases, they just fly that thing away and crash it. Yeah. So here it is on Mars, and that's the landing of these rovers. So I think that's really cool. It's a little bit different kind of mechanism than we study, where we have like cranks and whatnot, but you could use the same tools to study this. Any questions or comments on this? Yeah. Okay, that's all I wanted to show about that. We're going to get into vector loops again here. Lights are coming back on. Okay, so here might be a really big question you need to ask yourself for every vector loop analysis problem. How many loops am I going to use? Most mechanisms, at least ones that that I'm giving you, could be solved in 1 or 2 loops. Although a bigger mechanism with more components attached, you could use more loops. 2 is not a limit. So you could consider that even for simpler mechanisms, you could use more loops, and we're going to kind of see when it's advantageous or required to use more than 1 loop. So we already know that to be solvable, we have some requirements. So each loop must meet some requirements to be solvable. We've gone through that process before. So we know that our inputs, number of inputs, these are our independent variables. In vector loop language, those are independent variables. We set them independently. They don't depend on anything. Those are the inputs. This needs to equal the mobility of the mechanism. Right, if our mobility is 2 and we only have 1 input, it's not specifying what's happening with that mechanism. Okay, so that's our first criteria. That one should be pretty straightforward. When that one's violated, you'll kind of just see that. Second requirement is that each loop must have no more than 2 unknowns. Each loop must have 2 unknowns. And those are our dependent variables because they depend on the inputs. So each loop, right? So if we have more than 2 unknowns in a mechanism, clearly we're going to need more than 1 loop. We won't be able to solve that with only 1 loop. So let me give you an example of a mechanism. So I'm going to draw a 4-bar with some additional elements to it. And we're not going to solve this one in detail today. So here's our 4-bar. We may say our input here is theta 2 dot. And we know this mechanism has a mobility of 1. So 1 input will do the job. It'll set the state of the mechanism. And we've solved these problems before, right? Using, we haven't solved it using a vector loop method, although next time we will. Turns out this one is one example where there's 2 solutions. But we're going to ignore that for now. But what if I add an additional element to this 4-bar? So there's link 2, 3, and 4. But I'm adding 5 and 6. So the exercise you should do for yourself to decide about what to do with loops is let's count up all of our unknowns and just see how many there are. Right? And you could kind of imagine as you're doing this, you can kind of design your loop. So this mechanism, like we can attach our vectors. Like obviously we would attach them along here. Let me just attach some vectors to various lengths. Those are some nice ones that capture the motion there. We could make a loop here if we wanted. To finalize that, let me just, so R5 is along link 5. And then link 6, we'd like to track the position of that somehow, right? And maybe the goal is to calculate the position of link 6 here, left and right. So you could design a vector that captures that position, like the horizontal position of link 6. So let's actually do that. Let's come down. I'll call that R6 here. That's the horizontal position of link 6 from that reference point there. OK, and I'll call this just R7. The height is a constant. OK, so that one's a constant. So let's just list all of our unknowns. right? Every one of these vectors, we have 7, and I think like that, those should be able to describe the problem. Right? Those kind of capture every element of the motion. So some combination of those in 1 or 2 loops should be able to solve it. So let's list out what we don't know. R2 is our input, so that doesn't count. R3 and R4, those have constant length, but their angles are changing. Okay, so right off the bat, we can see the 4 bar by itself, without 5 and 6, we already have 2 unknowns. So that should signal to you, like I've already made a loop, and that one's going to be solvable on its own. Just this thing right here could be one loop. But let's just keep listing our unknowns and see how many others we have. R5 has constant length, but its angle's changing. So theta 5. Okay, and well, we better keep track of our constants because we want to make sure we get all of them, right? Because we're going to try and decide, clearly we're going to need more than one loop here because we have 3 already. We're going to try and decide if 2 loops is going to be enough. So we've got to keep track of everything. These are the ones I already said. Some of these lengths. And R1 is constant as well, length and angle. What about R7? R7 moves here, left and right, with link 6, but its length is constant, and it's always vertical. That's kind of how we defined that. I define that as vertical, so that's just a constant. Okay, so we have a lot of constants here. And one thing's missing, which is the length of 6. So that's like our x position, our horizontal position of the output, length 6. Okay, so they should add up, including the input. We have how many? Is it 7? 1, 2, 3, 4, 5, 6, 7. 7 vectors, so there should be 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Input makes 13. I'm missing 1. 6, yeah, theta 6. Theta 6 is always 0. So that goes here. So that makes 14. So that's everything. So we've categorized all of our variables as input, theta 2. Unknowns, these are our dependent variables. And constants, which are the easy ones. Okay, so we have 4 unknowns, 4 dependent variables. 4 dependent variables. So right off the bat, you should see that and say, clearly we have to have at least 2 loops. 2 loops are required to solve this. You could use 3 loops even, but at least 2 is needed. So 2 of these for each loop. If you designed a loop, a single loop, you could do that. You could do that. You could design a loop that went around here, around all the way, and back to the beginning. You could design one big loop, but it would have 4 unknowns, 2 equations, 4 unknowns. You wouldn't be able to solve it. But if we design 2 loops, and I think this one, I think it's pretty clear like what a logical loop would be. Loop 1 would be this, the 4 bar. So let's write out the equation here. 2 plus 3 minus 4 minus 1. So there's our first loop, and that's just a 4 bar. And that's going to be the best trick or technique that you can use in studying more complex mechanisms, is look within your mechanism for something simpler, like a 4 bar or a slider crank. And in fact, you already will have solved those. We've already solved a slider crank. We've solved an inverted slider crank, which is like a variation on the slider crank. Next time, we're going to solve this loop 1 for a 4 bar. So you'll have that solution, and you know what it looks like, and you can just kind of crank through it really quick. That's our loop 1. Oh yeah, so loop 1 is going to have unknowns, well, independent variables, inputs is theta 2. And dependent variables, the unknowns, those are going to be 3 and 4, theta 3 and theta 4. So you'll have 2 equations, horizontal and vertical components, and the two unknowns, theta 3 and theta 4. So you'll be able to solve that by itself. And now we can design our loop 2. On loop 2, we actually have some options. And the key is loop 1 has some outputs, right? Theta 3 and theta 4. Those are like the outputs. That's what you solve for in loop 1. And you can solve loop 1 on its own and calculate those. And one of those should become the input to your loop 2. One of the outputs from your first one should be an input to the second one. So we have an angle of length 3, an angle of length 4. So the simplest loop would be just this right side, 4, 5, 7, 6. I'm going to go clockwise around. 4 plus 5 minus 7 minus 6. Okay, and this is, has an independent variable of what? What's the input to this one? The input needs to be one of the outputs from our previous loop. So they share R4, right? They share R4. So the independent variable, or the input to loop 2, is theta 4. And that actually gets plugged right in from loop into loop 2, from loop 1 into loop 2. And that's a good thing. That's how we can progress through our solution. First, we'll solve loop 1, plug it into loop 2. And the outputs now are dependent variables. We can look here at our unknowns. It has 5 and it has 6 in it, right? So theta 5 and R6. So we'll have two equations there, and we can solve for these two unknowns. So in total, we're going to have 4 equations, 2 from loop 1, 2 equations from loop 2, and we'll be able to solve for all 4 unknowns. The most complex problems, this one is not too bad, because loop 1 can be solved on its own, and then plug that into loop 2. You could have a really complex mechanism, theoretically, where you'd have to solve all 4 equations simultaneously, although that's not very common in actual mechanisms. So usually you'll be able to solve the first one and plug it into the second one. Any questions about our using 2 loops for this problem? Yeah?
Is the independent variable of loop 1 theta 2 or the ground?
Theta 2, thank you.
And then where is, that means theta 2 is an unknown with the other side, right?
The independent variable, those are inputs.
Oh, sorry.
Independent variable. I don't like that term. Independent variable. Think about like, yeah, you can set it independently to whatever value you want, input. Yeah. You could think of IV as input variable. Yeah. Any other questions about this? You could design a different loop too. We had a single variable shared. You could design a different loop too that uses R3 instead of R4. So your second loop could be, so this is like we'll call loop 2 star, alternate solution, equally good, but it's a little longer one. Could go all around the whole thing. 2 plus 3 plus 5 minus 7 minus 6 minus 1. That's loop 2 star. That would be another, that's a fine loop. It has more variables, so I would be attracted to loop 2 rather than 2 star for simplicity. But you could do that as well. And in that case, theta 3 would get transferred from loop 1 to loop 2 star. So theta 3 would be like the independent variable for your second loop. And theta 2 would also, you'd also know that. So you could think about it, you could almost think about it like this has 2 inputs, theta 2 and theta 3. You could come up with another loop. You can think of whatever crazy loops you want that use these vectors. As long as there's 2 unknowns, you'll be able to solve it. Okay. Very good. So this is the case where 2 loops is required, right? A single loop is not able to solve this problem. But we're going to look at, we didn't go through the full solution for that. We'll do the 4-bar next time, and you could try. The second loop is really a slider crank, right? It's just a slider crank. Loop 2 is a slider crank. So we've actually already solved loop 2. We have different names for the variables, but we've already gone through that solution. And loop 1 is the 4-bar that we'll do next week. So this is our question. When do we want to use more than one loop? So that's our main criteria. But when do we want to use more than one loop? We have our first reason. That's when our number of dependent variables or unknowns is greater than 2. That means 2 loops are required. Okay, so you don't have any choice. And in that case, the output of the first loop, so the dependent variable of first loop, of loop 1, becomes your input for loop 2. Okay, that's how you should think about designing those. But there's a second case when we might want to use more than one loop. And that is, and we're going to look at an example and see why it might help us. If our number of dependent variables equals 2, but our loop is too complex, or we look at it and we say our loop's getting pretty big. Loop is complex, or not describing the output nicely. Not describing the output easily or logically. And we'll look at what I mean by that in a second. Then we can optionally, you have the option to use a second loop. So let's look at that at a case. We're going to look at a real mechanism. We're going to look at the same mechanism as we studied last time, which was our inverted slider crank. But I'm going to add an additional point to it. So here's the slider crank that we studied in lecture. Our input was on link 2, the angle of link 2. And the output last time was the rotation of link 3 and the slider going up and down. So we studied those and we designed a loop which went 2, 3, 1. It was just a triangle, and we saw that just the cosine rule described that. It was very simple. But what if we add an extension and an additional point of interest? We'll call this point C out here. And this is something that I've done a lot, right? I kind of spice up a mechanism by adding an extension. And the reason that I often do this is because it comes up really frequently in real machines that the base mechanism may be quite simple, but the output location isn't right along one of these lines. The output, or input maybe, is off on some extension. And it slightly modifies the behavior of the link, right? And maybe your mechanism needs to be hidden away. Like maybe this is a piece of exercise equipment and the ground it needs to be like underneath the machine. And this thing sticks out and you put your foot on a little spot there. Right? So that would be, that's how these are used really frequently, for the output to kind of extend out from the machine. Anyways, our goal here for this analysis would be, for that input, let's find like a position or velocity of that point, or acceleration. So we're going to try and decide, can we get by with just one loop? Do we need 2 loops? Or would it be optional to have a second loop? In this one, Taha studied a similar problem in tutorial. It was a different mechanism, but it had an extension like this, and he solved it using 2 loops. But let's think about whether that's actually required for this one. Okay, so let's put out all of our vectors on that we used last time. R2 and R3 and R1. That's what we had last time. And we could just add some more vectors. So we want to get out to point C, and we need to, there's lots of ways of getting out there. You could do like a triangle out there. I think it's a little bit simpler. I'm going to use red for my new ones. It might be a little simpler to put vectors right along here. So that I'll call R6. This one I'm going to call R5. And if I get out there, I need to complete a loop, right? So we have to get back. So I'm just going to go back right along the same link. Okay, and what if instead of using R3, we use these red ones? So let's kind of try to replace, need to keep, don't want to use any variables over again here. 2, 3, 4, 5. I need to call this 7, I guess. Yeah, so, okay, so here's some new vectors. That goes to all of our points of interest. So let's see if we can design a loop. Clearly we can, a single loop to go all the way out there. So this is going to be our single loop case. So we're just going to start here at O2, and I'm going to go clockwise around. We're going to go 2, and then we're going to go 7. Then we're going to go out to C by 4, 5, 6, and 1. Okay, so we went around the perimeter and I skipped 3. Right, but 3 is the same as 6 plus 7. 6 plus 7 is the same as 3. Okay, so this is a single loop, right? Single loop, and you may say, oh no, we have like a huge number of unknowns here. So let's track them out. Let's get our constants and our unknowns and see, is this going to be solvable or not? Okay, so we already know our input is theta 2. That's our independent variable. Dependent variables, that's our unknowns. Okay, so we just need to go through everything here. Constants, let's just start with 2 and then go through 7, 4, 5. Okay, so 2 as a constant. 7. 7's a little tricky. It's right here. And the length of 7 is going to change, right, as that slider moves up and down. The distance between this point, I'll call it point D there. The distance between D and call that B. D and B, that distance is going to change as the slider moves. So R7 is a unknown. It's like R3 before. R3 got longer and shorter. Now it's going to be R7. Okay, what about theta 7? Theta 7, that's an unknown. But if we look at that, we'd say theta 7 is the same as theta 4. Or sorry, theta 3. So that's like how we solved it last time. It's the same thing. But we need to include it as one of our unknowns here. Okay, that's 7. Now we go to 4. So 4 has a constant length. But what about its angle? Its angle varies with length 3. So you may be tempted to put it as an unknown. And you could, if you didn't know anything about it, you could put it here. Or you could notice that it's always perpendicular to 7. Right? That's the design of length 3. If you know theta 7, you know theta 4. It's just, what would it be? 90 degrees more, right? It's 90 degrees counterclockwise. So that's like a relationship that we know. Theta 4 equals theta 7 plus 90 degrees. So that's like an additional relationship that we know. So it's up to you to decide if you want to call that an unknown, you can. And you're going to need more loops to solve for that. Or we already know this relationship. So it's probably better just to use your relationship. It's very simple. And now theta 4 is not going to count as an additional unknown because we already listed theta 7. So it's not necessarily constant. So maybe we'll make up a new category. And this is, the book doesn't call it this, but this is how I like to think about it. Additional knowns, because we have some relationship. Theta 4 equals theta 7 plus 90 degrees. Okay, so it's not an unknown. Once we already have theta 7 as an unknown, theta 4 can be calculated from it. And a quick look, you can see 5 and 6 are going to be the same story, right? So theta 5 is going to be listed here. And that would be opposite to 4. Or we put 7 here as our dependent variable. So let's write all these in terms of theta 7. So 5 would be 7 minus 90 degrees. Okay, and 6 is our last one. And that's the same as 7, same direction. Okay, so we have 3 of those. In fact, 7 is the same as 3. So you can convert between all of these. Okay, so none of those count as new dependent variables. That's everything here. Let's keep track of where we are now. We added 4, 5. We added 4, 5, and 6, but we didn't. Yeah, we put R4 here. R5 is a constant, and R6 is a constant. Just keep track of everything. And R1 is our final vector to get back to the beginning, and that's constant. Whew, so there's a lot, right? We have how many vectors? 1, 2, 3, 4, 5, 6. There should be 12 parameters, 12 variables. We have our input, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we kept track of everything. And how many unknowns do we have? Just 2, theta 7 and R7. So this one loop is big, it's complicated, but because of these knowns, these relationships between some of our vectors, it turns out we only have 2 dependent variables. So a single loop can solve this problem. Can solve this problem. And you could go through that and you could solve it. So that's fine. One problem with this is that once we solve it, right, we're going to get the answer in terms of R7 and theta 7 and their derivatives, R7 dot, theta 7 dot. And those are not directly useful. Right? Those don't give us our answer directly, velocity of c. So once we solve this, we have to do a second calculation to calculate velocity of c. And it's not terribly complicated, but it's an additional step. So even though we can solve it, we need an additional equation. Or I called this last time the interpretation of the answer. Remember last time we were talking about the slider motion and positives and negatives and what those meant? Here we're going to have to do an additional equation to calculate velocity of c. And you could say, okay, this is almost like vector loop way of thinking. C, we could start at this ground point and do 6 plus 5. That's going to be the location of c. So you could write out a vector for velocity of c is, well, one way you could write it is R6 dot plus R, what are they, 5. So calculate those two. Or if you wanted to put it in like the x, y coordinates, it would be, we don't have a great way of writing those. So that's the x coordinates, the horizontal components of R6 and R5 added together, and the y components. So you can do that. That's how you'd have to if you use a single loop, you'd have to do that, for that loop, you'd have to do that to kind of interpret the answer and give an expression for velocity of c. So that's fine. It's a fine process. It's solvable. 2 unknowns, 2 dependent variables. We have these 3 additional equations, and everything's fine about this. Any questions about this option? An alternate option, yeah.
Would C also be BC, would that also be R4 dot plus R7 dot? Is that equivalent to what you just wrote there? No?
So VC, you're proposing an alternate expression for velocity of C, which is R4 dot plus R7 dot. No, because this point here is moving. So you're expressing, what you're expressing is B relative to C. That's what that is, velocity of B relative to C. And this is a nice, you can always kind of convert between our different solution language methodologies. This is like converting into velocity polygon language. B relative to C. It's a vector from C to B. Yeah, so you could do that. You could use that to check your work from multiple methods. Yeah, another way you could do is like, starting at this point, 2 minus 7 plus 4. That would get you velocity of C relative to this point. 2 minus 7 plus 4, velocity of C. Okay, so this is our solution for single loop. But as I mentioned before, this is a case, situation number 2 up here. The number of dependent variables is 2. So if we want to, we could solve this with 2 loops. And let me show you a proposed 2-loop design, which I think is actually easier and more logical to solve this problem. So here's a 2-loop solution. Okay, and it's up to you as the engineer to decide what you want to do. We're going to divide the problem into 2 pieces, basically. And that's going to make each piece simpler. So we're going to have 2 simpler loops. Okay, so let me put my points. I'm not going to draw the whole mechanism here. O2, B, D, O4, and now here is C. Okay, so that's the key geometry of our mechanism. I'm just going to draw a new set of loops here. Let me use my 2 colors. So the first loop, let's make it as simple as possible. Let's just make it that base triangle. This is the one that we solved last week. So we'll call that loop 1. Okay, we know it has 2 unknowns, 2 dependent variables. That's the length of 3 and the angle of 3. That's what we solved last time. And the input, of course, is theta 2. Now we're going to add our second loop. And this time, rather than just putting a bunch of vectors on, my big suggestion to you on loop design is think about what your solution looks like and design your loop, design vectors that give you your solution directly. That can simplify your problem a little bit and eliminate this last step of having an additional equation afterwards. So I'm going to design 2 vectors that give us the position of C relative to a base point, like O4. So let's just give X and Y position of C. And I'll call those just Ry and Rx. Okay, and that is going to have the great advantage that we can write velocity of C. It's just going to be x plus y. So Rx dot and Ry dot. And those are things we can solve for directly. Our loop equations, those will be dependent variables. We can solve for them It's just the length of x, vector x and y. Solve for them directly, and we have our answer without that additional interpretation step. Yeah?
I just don't understand how that's a complete loop. Like just
Oh, it's not a complete loop yet. Yeah. It's just like I'm starting with the answer, and I'm starting to design. So now we need to complete the loop. And it needs to still capture the motion of link 3. And it's still, remember our last example, we had an output of the first loop became the input to the second loop. So we can look at these, like these were from last time. This time our outputs are R3 and theta 3. So let's use this theta 3, angle of link 3, as the input to our second loop. So we output it from our first loop, and it's going to come down to our second loop. And we really just want to capture the angle of it. So let me just design a simplest vector out along that. So 3. I'll call those R4 star and R5 star because they're different than R4 and R5 over there. Although, why don't we just use the same ones? There we go. That's a good idea. We can stay consistent. R6 and R5. Perfect. OK, so now we have a complete loop, right? The red one. So I'm going to go clockwise from 04, R6 plus R5, minus Ry, minus Rx. OK, unknowns and knowns, independent variables and dependent variables. Our input to the second loop is going to be the output from the first loop. That's theta 3. So our input, theta 3, is the same as theta 6. Right? I put that along link 3, same on purpose. So we can say theta 6 is the same as theta 3. So that's our input to the second loop, output from the first loop. And unknowns, of course, are going to be this output, Rx and Ry. And everything else is going to be constants for this one. Other questions about this approach? So each loop is simpler, right? It's much shorter loops. Loop 1 is trivial. It's just a triangle. We've already solved it. You'd use your cosine rule, but we already solved it. So we already had that solution, and we can just design the second loop to get the output that we want directly. Let me just, we don't have enough time to go through the full solution. I'm thinking if I can give you the answer. I use different vectors than I did before, so I can't write the answer for you directly. But this one just has 2 dependent variables, and it's a pretty straightforward geometry. Oh, OK, last thing. This is what I wanted to add. 5 and 6 are perpendicular to each other. So just like we did over here with these known equations, we need one of those for this second loop. 5 and 6 are related. So the angle of 5 is, I'll let you try this one. Is it, it's perpendicular, so it's plus or minus. Which one is it? Something is 90 degrees off. It's clockwise. So we go theta 6 clockwise. So clockwise is negative direction, right? So we need to do minus. So that's like a known for loop 2. So that's not going to count as a dependent variable. It's not going to count as an unknown because we have that equation. And theta 6 was our input directly. OK, any other questions about this? So as the designer, as the engineer, as the loop designer, you can choose. And you can kind of look at these 2 and think which one suits you. A lot of it may depend on what you already know. If you can identify a mechanism component that you've seen, like a single triangle, or a slider crank, or a 4-bar that you already have a prepackaged solution for, bam, that's your first loop. Add on to it for a second loop, and that's going to make for a quick, easy solution. That's all for today. Thanks, everyone. Next time, we'll do our last vector loop lecture.